Here. Again, my name is Jin Tai Ding, and I'm actually a mathematics professor at University of Cincinnati. I'm also the vice chair of ABC Mint. I believe my partner, Andy, was here maybe a month ago, 2 months ago? 2 months ago, yeah. So he's my business partner in the sense that he's in charge of business, I'm in charge of the algorithm side. So today, I think my main job is to tell you the story about post-quantum cryptography and how I get into this. So this is what I intend to talk. Okay, so let me start. So the story, this quantum proof cryptocurrency or quantum proof blockchain, we did not develop it. So the story is a little bit subtle. Anyway, ABC. So first question, what people always ask me, what is ABC? ABC, we don't know what the meaning of it. Okay, just a name. Okay, you can call whatever you want. Somebody called it advanced Bayesian currency. Somebody says algorithm, blockchain, cryptography. So these are not important to us. It's just a name. If you want to call a different name, we don't mind. Okay, so this is a new quantum proof blockchain. And the most important thing I want to emphasize is there's a new signature inside. And this signature we claim to be quantum proof, has a potential to resist quantum computer attacks. As Richard said earlier, actually NIST had a call for standard with a deadline of November 30, 2017. We're now actually in the second round already for the post-quantum standard for the US government. So NIST stands for National Institute Standard of Technology. So this belongs to the Commerce Department. And this is actually the US government agency which makes security standard, not NSA. So the US law is very interesting and subtle. Let me repeat, okay? The security standard is actually decided by Department of Commerce, not NSA. Okay, they make standard. And according to US Constitution, NIST supposed to listen to advice from NSA. I think everybody knows what NSA is, right? And the exact law is not very clear how this role should be played. Okay? Mm-hmm.
Best place to stand is
okay,
here.
Sure. Okay.
Yes.
Okay, good. Okay. So anyway, this new quantum proof blockchain also has a new POW based on solving a set of random quadratic equations. So it's a bit different from the standard Bitcoin design. And I'll explain a little bit about why we do this. And it was launched already on June 18th. It's been running for more or less a year. Okay, if you're interested, you can go to www.abcmint.org and you can download it. You can run it already. Okay, so let me. Okay,
Next page.
Next page, please. Yes, thanks. Okay, here I still would like to mention a few words about Bitcoin. Okay, one thing, very important thing is we all know Bitcoin is an open ledger. And it's decentralized, anybody can participate, it has pretty good privacy and pretty efficient. But the reason why we call it cryptocurrency is because Bitcoin is basically is built upon fundamental cryptographic algorithms. Okay, the two things I would mention is the ECDSA, which is the elliptical digital signature, and which belong to the family of public key cryptography. Okay, another one is a hash function. Hash function is used for two purposes. Number one is to create your address from public key. Number two is for POW. Okay, and the reason you can see why it's called cryptocurrency because it's based on cryptography. Okay, and then next please, yes. Okay, and as the previous talk already talked about it, POW. Why do we do the POW? The POW purpose is to what? In a decentralized system, you have to synchronize the data. That's the sole purpose, to get a proper history of the data. That's all. Okay, and I have to add one more comment on this. I mean, Bitcoin created something very important in human history. This is called immutable record, which means that the record of Bitcoin, you can destroy it, but you cannot change it. If you change it, everybody can see it easily because the nature of the design. Okay, it's immutable. Of course, it has a risk of a 51% attack, but this is something very natural in some way in terms of the democratic system or in any system, you have something similar to that because it's decentralized. I don't think this is a defect coming naturally to the system. This is what I believe, even though we don't like it. Next page, please. Okay. And then I give you first this number. Does anybody know what this number is? It's a huge number, I know.
Prime.
No, it's a product of two primes. I think you can guess what it is. So this was once what Microsoft used for software update. So we all, in our computer, your computer often asks you, and now we are doing Microsoft update. You say, yes, you agree, right? But how do you know the update from Microsoft? How do you know?
Signature?
Exactly. So there is a signature attached to Microsoft software, and it's signed with the public key of this guy. And this is the RSA signature. Okay, so imagine if you can, so this is a number which is a product of 2 prime numbers. So which means for a long time, if you're a very smart person, if you can factor this number, you can fuck the world. Which means what? You can send any software update, and your computer will what? Will think it's from Microsoft. For example, you can send a command, delete the hard drive, your computer will execute it. Agree? Okay? So this is a next page, please. Yes. Yeah. So this is for. I mean, you can see easily if you see this is an old page. You can see that this is coming from the Windows. You know, the Windows XP Professional with the Summons Package 2, and this is actually RSA digital signature signed. Okay. So which means whenever your computer do a software updates, they will check with the public key from Microsoft. Make sure what it is from Microsoft, and all of your antivirus software does exactly the same thing. Please, next page, please. Okay. Okay, so this is next, please, yes. Okay, this is a little bit, yes. So next, please, yes. Okay. So the mathematics behind is very simple. Is it what? Integer factorization is a hard problem. Okay? So the fundamental principle is that we, given 2 large prime numbers, anybody here can easily multiply them, get a new number, which is n. But given n to you, it is computationally invisible if it's large enough to find the P or Q. Okay, so it's based on this hard mathematical problem. I mean, one example is 15. 15 is 3 times 5. Of course, this is just one example. We're using much larger numbers. And the previous number I showed to you is has about 2,048 bits, about 700 digits. Please, next one. Okay, so yes, great. So what is happening now? How many of our modern society actually live in a new world? I would call it in math we trust, not in God we trust. Because we believe factoring is a hard problem. That's we put everything into it. Really. It's really all the security, all the internet security depends on mathematics. That's it. And if there's a super smart person, he really can destroy the whole world easily. Just a finger. Okay, and so what I want to say is Bitcoin is not only one, right? Our whole system actually relies on the cryptography. Next, please. Okay, and the idea of public cryptography was proposed by 2 guys here, and this is Diffie, and that's Hellman. And Hellman is a professor at Stanford, and Diffie was his student, and they won Turing Prize in 2016. So it's Diffie and Hellman who proposed this idea of public key cryptography. Okay. And then the first person, next please. Yeah, the first people who managed to make it, the first system is RA system. These are Shamir, Rivas, and Edelman. They invented the concrete system. So Diffie-Hellman is very interesting. They proposed an abstract idea of public key cryptography, but they could not do it. It is actually RSA who invented first. Okay, next one, please. Yeah. So what is public key cryptography? Okay. So what's the difference between public key cryptography from traditional cryptography? So before public key cryptography showed up, what we do normal cryptography is what we call symmetric cryptography. For example, Enigma machine or the AES we use now. Symmetric crypto means what? In a communication system, the sender and receiver have exactly the same keys. Okay. So this also means what? The German U-boat, before they left the port, they must have exactly the same code book with the headquarters and with every single submarine in the fleet, so they can talk to each other. And this, in mathematical context, this is called key exchange, which means they have to have a prior key. Okay, and this is durable for states. Right? You have how many submarines? 150. We can meet together and decide it. Okay, and things changed quickly in 1960s. Go ahead, please. Next page, please. Okay, next. Okay, so next 2 parties must do key exchange. Next one, please. Yeah. Okay, in 1960s, now we have large computer networks. okay, appeared in US, in Europe, and so on. And between any two computers, if you want to talk securely, you must what? Do a private key exchange. And that's impossible, right? Suppose you have a computer here, there's a computer in the US. How do you do this? So Diffie, that is actually Diffie who is the really driving force behind this. He wanted to find a way to solve this problem. How to build a secure communication system for computers, for large-scale network. That's what he wanted to do. Okay? Okay, so next please, yes. Okay? And that's his proposal. His proposal is we should do public key cryptography. Okay? And in this case, it's not symmetric anymore. It's asymmetric, which means this is a system. Yeah, next page, please. Yeah. This is a system that you have two sets of keys. And the example I gave you earlier is a case of an ISA system, is that the public key is number n, which is equal to p times q. This is a product of two prime numbers. And the number r, which is co-prime with p minus 1 times q minus. So this is a public. And then underneath, there's a private key. I wrote dpq. Actually, d is enough. But d is computed from p and q. As long as you know any one of those is enough. And the first set of key you use to receive message, which means I publish on New York Times. You see the Jin Tai Ding owns this public key. Therefore, what? When you want to talk to me, you what? You use that encrypted message sent to me. Openly. And only I, because I'm the guy who knows the P and the Q. Theoretically speaking, only I can read it, so I decrypt it. And that's how it works. But practically, things work very different ways. RSA is never used for encrypting messages. It's always used to encrypt keys. It's actually used to help us actually keys. We never use encrypt message. Why? It's too slow. If you want to play computer games, especially video games online, you cannot use public key cryptography. You have to use symmetric cryptography, string cipher or block ciphers. Okay, and next piece. Okay. And in our modern communication system, it's used already in our network. For example, it's used in SSL, TLS. Okay, so this is about secure communication. But there's another layer of it. Go to the next page, please. Is authentication, which means on the open network. Okay, when you talk to each other, one thing very important is the message you received is indeed coming from a guy who claims sent to you. So this is how digital signature was invented. Okay, digital signature is invented in the same way as the encryption system, meaning what? You have two sets of keys. One is public, one is private. And the public key is used to verify the authenticity of the message. And the private key is used to sign the document. Okay, in the case of ISA, again, it's the same. In the ISA digital signature, again, the public key is N. The private key is P and Q. And the security relies on the fact that it is difficult to factor N. That's it. Okay? And as I explained already, where we use it before Bitcoin come up is used in software update, used in legal document signing, and used in voting. Okay, next please. Okay? And now comes the quantum computer threat. Okay? So the idea of a quantum algorithm was proposed in 1995 by Peter Shaw. Nobody paid attention. We didn't care because we didn't know if it works or not. But in 2000, there's a guy called Isaac Tron. He spent $15 million to show 15 equal to 3 times 5. But he used a quantum algorithm. 2000. And that's the time I decided to work on this. Okay. Year 2000, I shifted my research. My research originally was in algebra. And I saw this, I said, this is interesting. Okay, so at that time, what the Tron had is I think it's 5 qubits or 7 qubit quantum computer. If you can scale up, then you can defeat ISA and elliptic curve digital signature. Okay, the Shaw's algorithm solves actually a more general mathematical problem called finding a period of function. And this algorithm can solve both factoring and discrete log problem on the elliptic curves. Okay, so next please. Okay, again. People always ask me, is a quantum computer a real threat? First, I showed you, right, it is possible, because somebody did it already. But scaling up, is it possible? I don't know the answer, but this is slides I copied from Professor Mosca, okay? And he copied from somewhere else, from Physics Journal or something. So they divide the building quantum computer in 7 steps. we are more or less here, or maybe a little bit up. Okay, so this is his interpretation. Okay, yeah, next please. So when I started to work on this in 2000, I shifted in the field in 2000. Nobody paid attention. For 15 years, nobody cared. But for whatever reason, in 2015, on August 2015, suddenly NSA announced on their webpage, and the statement is here, IAD. IAD is Information Assurance Division of NSA. So IAD will initially transition to quantum resistance algorithm in not too distant future. So out of nowhere, NSA suddenly decide that the US government wants to build the next generation standards. So here I would like to mention one thing about standards. So in the US at least, the standards are not mandatory, which means US government make a standard, you don't have to adopt it. But the rule is that if you want to sell anything to US government, then you must use this standard. Because of that, it becomes a de facto standard in the US, and more or less later become a global standard. So that's what happens in general. Next, please. So the research area I work on is called post-quantum cryptography. And this is very different from quantum cryptography. So this is also something I would like to explain a little bit, okay? When people talk about quantum cryptography, they are talking about something coming from physics. They're using physical principle on it. Okay, in particular, for example, QKD, quantum key distribution. And they're using fiber optics, okay? And the security relies on the fact that if you eardrop on the fiber optics, they can detect it. That's their principle. It's very different from what I'm talking about. So what I'm talking about here is the post-quantum cryptography says we use mathematics. We want to do exactly the same thing, but use different mathematical principles. Okay, at the moment, there are 4 different families of post-quantum cryptography systems. There are some other minor designs I did not add here. Anyway, one is code-based design. This is based on error-correcting code. And there's also hash-based design. This is only for signature, for stateful signature. And this is based on the security hash function. And also lattice cryptography. And the last one is multivariate public key cryptography. And that's where the rainbow design is based on. Okay, so these are the 4 main areas of the, okay. As I said earlier, the NIST standardization process, the first round, the deadline was November 27, and the second round is, the deadline was March 2019, which means about 3 or 4 months ago, okay? In the first round, there are about 80-something submissions. Right now, we have 26 left. Among the 26, 17 are key exchange algorithms, which is to build shared keys. And 9 of them are digital signatures. And Rainbow is one of them. Okay? And at the moment, of course, it's a very exciting area for research in post-quantum cryptography, and people pay attention now. And we just actually had the 10th International Conference on Post-Quantum Cryptography in China in May. I was one of the co-chairs. Okay, so this area is extremely popular, extremely hot now. Okay, next please. Okay, and now I would mention a little bit, I would like to discuss a little bit about the quantum threat on Bitcoin. Okay, so this is something I think I should explain better probably than before. And it is true, first, that hash function actually is more or less secure and the quantum computer attack. Because the algorithm that can be used to attack hash function is called Grover's algorithm. It has what is called square root speed up, which means whatever the complexity before, you can speed up become square root of it. But in the case of factoring and discrete log, it is an exponential time improvement in principle. Okay? And so then people will say, hey, if you only see my address, you cannot get the public key, which I agree. Then how can you attack me? Number one thing I would like to say is that at the moment, 70% of addresses already have their public key exposed. Meaning what? If you reuse the same key, then what? Well, then we know the key attached to the address. So which means 70% of the owner's Bitcoin is gone if you have a quantum computer. You can steal them freely at the moment. Okay? And just like, and number two is that, so therefore, then say, okay, from the white paper of Satoshi, we know that you should only use your key once. So you say, hey, what's the big deal? I just use my key once, next time I use different key, so therefore what? I never reuse the key. Then there should be no problem, right? The answer is no. The answer is no is because the nature of design of Bitcoin. Because when you spend the money, what you do is you broadcast your transaction. When you broadcast your transaction, you have to tell people your public key so we can verify it. And as we know, the network can be congested sometime. Right? So for example, with the transaction, we know every 10 minutes we can do certain transaction. If your transaction is not executed during that time framework and it's hanging there, and as an attacker, I can see your what? I can see your public key already. I can use that time frame what? If I have a quantum computer, can calculate your secret key and steal your coins. So therefore, the design of Bitcoin tells us you cannot. And also we can do what is called an active attack, which means if I see a huge transaction, I can jam it, meaning I can send a lot of small transactions with high fees, such that I push you out, such that your transaction will be delayed. Then I can use my quantum computer to compute your private key and steal your coins. So in my opinion, no, you cannot deal with this problem. So therefore, you must do quantum proof if there's a quantum computer. Okay? Another thing, just one second. Another thing, people say, hey, you already told the story, right? All the nations, all the states, all the banks are using what? Public key cryptography. Why do I steal Bitcoins? Why don't I attack banks? Why don't I attack state? My answer, no, you don't do that. You know why? Because when you attack banks, when you attack states, you have liability. But here, in the design of the Bitcoin, if I have a quantum computer, if I steal a Bitcoin, in my opinion, it's legal. I didn't do anything. Do you agree? I don't know if you agree with what my opinion. Right? You are supposed to keep your secret key secret. Nobody should know. Somehow, I have a quantum computer, I just computed it. I got it. And then I take the Bitcoin away from you. But in my opinion, it's nothing illegal. So therefore, Bitcoin will be the first test ground for a quantum attack, in my opinion. Because there's no liability. Okay, so next, please. And actually, I started to think about this about 2013, 2014, because I got to know Bitcoin from my son. Okay, when I saw it immediately, because I have been doing post-quantum cryptography for a long time, so I realized immediately, hey, there's a problem. And an easy solution is to do a drop-in solution, which means I have an elliptic curve digital signature. I just grab one of the post-quantum signature and just replace it. Is that it? And the answer is no. The new digital signatures, the new quantum proof signature normally has the following property. Either the public key is very large, or the signature is very large, or both of them very large. So if you do a drop-in replacement, you will blow up the transaction size. Because in the transaction, you must put the signature there. You must put the public key there. You will kill the chain, basically. Okay? And we develop ways to solve this problem, to manage to put the rainbow there. And we can maintain more or less the same efficiency. Okay? And one more thing is very important is state. Okay? For hash-based signatures, most of the designs, the ones actually being standardized by ISO, are called stateful signature. So I want you to keep in mind this word, stateful, which means those are hash tree-based signatures. When you sign, you have to remember at which position you signed last time. And you have to sign the next signature have been done exactly in the next position. And if you do not remember where you signed before and get in disorder, then the signature is broken. So therefore, if you want to use a stateful signature, this is a big trouble in my opinion. You should not use it, because if you have one wallet on two different devices, and you're killing yourself, because you have to synchronize all the time. So therefore, I don't think a stateful signature is a solution for this case. Okay? And the rainbow signature, I would mention one last word is rainbow signature. The most important property of rainbow signature is it has a very short signature. Okay, this makes things possible. Okay, and then I want to talk a little bit about POW. Okay, and I fully agree with the previous talk about POS and POW. Okay, okay, and I personally do not approve POS, and I have a different perspective. Okay, so in POS, more or less, your vote is decided by how much coin you have. Okay, and you have no cost, in my opinion, to do something bad. But POW, even if you have 51% of power, you still have to turn in your machine now. You still have to run all the electricity in not to do something bad. And that cost is very high, we know. And that prevents them from doing something bad small. Which means when they do such a thing, they have to consider cost. So from this perspective, I don't like POS at all. What's the difference between POS and bank? What's the difference? If you do POS, because POS, if a few people have the majority of the coins, they can do whatever they want with zero cost. In the case of POW, I like it. So people say, oh, this is a waste of electricity. I mean, I don't think this is a bad idea, actually. This is the reason why it's secure, I think. Because it uses scarce resources. This is what I believe. Also, and people talk about the green effect. So I also have a different perspective on this. Okay, I think we should use Bitcoin in the Sahara Desert. We should build power station in the Sahara Desert. And we should use it near a power station where in the evening, the electricity cannot be used properly. For example, I heard from some Swiss company, and they are actually enticed to move to the upstate New York. And right near the hydropower stations. Because in upstate New York, especially in the summer, no, not summer, I think it's in the winter, they produce too much power, nobody consumes it, and the network is overburdened. At that time, they actually pay you to spend electricity. So from my perspective, if you build a mining facility in the Sahara Desert, it's almost like you are moving the energy from the desert to the society, to our human society. Okay, so this is a POW. And then one more thing, what we do here is we modify slightly the POW system proposed by Satoshi. We use more or less same principle. So instead of doing hash functions, our proposal is that the challenge to do the POW is to solve random multivariate quadratic equations. If you find a solution, then what? You will be rewarded. So instead of just do hashing, you have to solve a set of multivariate quadratic equations. Okay, please. Okay, so I do a little bit more mathematics here. So what is so what is a multivariate quadratic polynomial? It's very simple. So you have a bunch of variables. You do quadratic terms and linear term and constant terms. And those coefficients are independently uniform chosen. And your job is to find a solution. Okay? The most important thing is that in mathematics, we can prove this is an NP-hard problem. This more or less tells us what? It doesn't matter how smart you are, you should not be able to what? Find very efficient way to solve it. Otherwise, the whole mathematical world will collapse. Okay? So this is a next, please. Yes.
Did you guys get that?
Is that okay? Okay. So again, so this is what I described, yeah? So in the end, you have to find a solution, which means you have to find a bunch of variables. You plug in every single one of them, it has to equal, all of them have to equal to 0. Yes, then you will be rewarded. That's how it works. Okay?
Next slide.
Yeah, next please, yes, sorry. Okay, so in the spectrum design, what we do is, in general, the challenge has the number of equations is n, the number of variables is n plus 8. Okay? And so it's NP-hard, and the most important thing is that the coefficients of those polynomials coming from the hash of the block. You just keep hashing it, and you get all those numbers. Okay, those are supposed to be random numbers. Okay, and one very important perspective is that the PIs, the coefficients change all the time. Why do I do this? So what is in my mind is to do something called ASIC resistance, which means I would like the problem change all the time, such that make it much harder to do ASIC. So that was in our mind. Okay, and then one more particular interesting about this multivariate quadratic equation is that it's actually extremely easy to compute. So that means on the chip, you cannot do too much in terms of optimization. Yeah, unlike hash function allows incredible optimization in the following sense, right? If you run hash function on CPU, then if you run on GPU, the efficiency improves about 5,000 times. And you go from GPU to ASIC, again, the efficiency increase about 5,000 times. So in this case, don't bother using CPU or GPU. It's completely does not make financial sense. Okay, and you ask me what's wrong with the ASIC machine running? So all of you know the mining pool, right? You know the mining pool, yes? So how many big mining pools now? Do you guys know? The big ones. Okay, 5. Let me take 5. So what does it mean? What's the percentage? Do you know what's the percentage they control the company power? The 5 pools. 70%. Okay. So we talk about 51% attack, right? What does it mean? These 5 guys, or these 5 companies, these fighting pools, actually what? They can easily perform 51% attack. Actually, they did. Do you know that they did? I mean, for a few instances, we did rewinding. Do you guys know? Okay. Anyway, look at the numbers. So the 51% attack has already happened. Actually, legally in some way. I mean, so Bitfinex lost 7,000 Bitcoins, right? You know what the Bitcoin did, right? They called those miners. Can you help me rewind it? Which means we are what? We delete what? Basically, we delete 6 blocks back. Okay, this is something we should be very careful about. So theoretically, Bitcoin is supposed to be decentralized. But the moment, and those 5, I mean, I talked to them, the 5 big pools, they actually are friends with each other. Okay, they can do bad things, for sure. It's a pretty scary part in this aspect. And we should solve this problem, I think.
You said the rollback happened already?
It already happened, yes. We just didn't pay much attention to it. Pardon me?
At which block number?
I forgot. They didn't give me the number. Yeah, it happened already.
How long ago?
2 years ago? Yeah, something like that. Yeah. Yeah, it's a rollback about 6, 7 blocks. How many blocks? I forgot. Rollback, how many blocks? Yeah, so this is one of the motivation for me to do new POW. I would like to develop something which ordinary people can participate, and we do not let the ASIC machine control the computing power. I think that's something we should do. Okay? Next, please. Yeah. So I mean, this is more or less what I would like to talk about. So our goal is, I mean, we didn't do it. Okay, this is very important. This is the story I have to make straight. So my partner NDI, we built a foundation. We raised some fund as a donation, and then we donate the money to an independent developer team. They have nothing to do with us. No legal obligation to us. Then they built this new thing, even though I designed the protocol. But they have no obligation to us. Okay, those are anonymous developers coming from all over the world. Okay, and so we hope this new thing should be a non-tenant secure blockchain and should be the start of this one. And so 2 main things, technical perspective, I said, is first we use rainbow signature. Number 2 is we use a POW based on multivariate quadratic equations, which is an NP hard problem. So therefore, we do not expect quantum computer to pose any real threat on this as well. Okay, so that's it. I think that's the end of my lecture. Thank you very much. Yeah.
Thanks very much, Professor Ding. Are there questions? Yes. Heads up. Watch out.
So we know that elliptic curve cryptography relies on the fact that discrete logarithm is hard to calculate. So what kind of cryptographic assumptions do you need for?
For rainbow signature, is number 1 assumption is the NP hard problem. Solving quadratic equations is NP hard problem. Okay. Yeah, but they are also relying on one more thing called a mean rank problem. Yeah, that's too difficult to explain. Yeah, so we have very good question. So all those things are based on assumptions, hard mathematical assumptions. For example, code-based. Code-based is based on certain error correction problem are very difficult to do. And lattice is based on certain lattice problem. For example, finding the shortest vector or a short vector in a lattice is very hard. Okay, there are different mathematical the principle coming different from the discrete log or factoring. Yes.
Hi, thank you for the explanation. A quick question with regard to time frame. When do you think that the quantum impact will start affecting, for instance, the current proof of work algorithms of Bitcoin? Is it going to be something like within 2 years, within a 5-year time frame, or 10 years, or even after 10 years? So maybe if you could elaborate a little bit on that. And the second part of my question would be, right now we know that on a a chain such as the Bitcoin blockchain, for instance, the value on it, and it changes a lot, is, let's say, 200 or 300 billion dollars. At a certain moment then, so that relates to the time frame, something will need to happen, probably a hard fork then, in order to make it quantum proof resistant. What are your thoughts about how that should happen for a chain such as blockchain, which is quite important in economical terms?
Okay, yes. So let me answer one by one. So number one question is basically, when does a quantum computer become a real threat, right? This is your question, yeah. So the answer is, I don't know. Nobody really knows. It's possible it's here already. I mean, there must be a reason why NSA does this. Do you agree? And why does NSA want the US government to move to post-quantum algorithms? There must be a reason. And if you look at history, they give us a pretty good hint, right? For example, Enigma machine, right? An Enigma machine was broken in 1940s, right? And when did we know that? 1970s? Right? So that's give you a hint, I think, about this. Okay? And if you look at the news, and you will know that is going on now. There are news every day about improvements quantum computing technology. So these are open news, right? These are in the public. And there are things behind, I think. And one thing for sure I know is that if I have a quantum computer, I do not want to tell anybody. Do you agree? Because I can read all your emails. Right, this is one thing. But next thing you should think about is the following. Why does the US government want to do this? So suppose you're going to make the standard in 3 years. That's their time frame. They want to finish in 3 years. I expect totally in 10 years, US will totally move to post-quantum standard. And think about it, the cost. Okay, this means what? From internet protocol, the fundamental internet protocol, everything has to be changed. I mean, the estimate cost is like, I don't know, at least one says at least $100 billion in the next 5 years or something like that. And that's, the cost is almost as high as Bitcoin, right? Or higher. Why do you do this? There must be a reason. Okay, another thing you should think about it, related to the answer for your second question, is the migration time. Suppose I already make a standard. And I think for the people here in this room, half are probably technical people, half are not technical people. The technical people probably will adapt very quickly. Non-technical people, it takes a long time, to do the migration. I think about elliptic curve, okay? Elliptic curve was more or less made in the standards about early 2000 already. It's only started to catch up recently. So adaptation standard takes a long time. Okay, that's one of the reasons why in terms of such a situation, you must prepare at least 10 years ahead. Now, this is also related to answer your question about Bitcoins. And you know there's a Bitcoin fight between, in the inner fights. So we were thinking about, at the beginning, we were thinking maybe help Bitcoin do this. Then we realized we'll give up. Because I have to say, the Bitcoin community is pretty divided. Whatever you propose, there will be people for it, there will be people against it. And look at the situation now. There are still 9 algorithms. If you propose to do quantum proof none for Bitcoin, for example, there will be, I think, 9 algorithms. For the 9 algorithms, each algorithm should have somebody supporting it. So I think the migration for Bitcoin will be very hard. So this is my opinion. Yes, it's nearly impossible because it's fully decentralized. So this is what I believe. Okay, I hope I answered your question. Okay, good. Okay, next question, please.
So you have a system of n equations with n plus 8 variables.
Yes.
Like, how do you solve this?
The best algorithm at the moment is brute force search. Just like Bitcoin case. You just search one by one. It's over GF2, over binary field. You just try one by one until you find one. Find the solution. That's the best way to solve them. Brute force search, just like Bitcoin, right? At this moment, that's what Bitcoin does, right? You just compute one until you find the one you want, and that's it.
How did you come to the coefficient of 8 plus 8?
This is because it's a very good question. Yes, because I want to make sure there is a solution. So n plus the 8 is coming from the calculation of n plus 8, which means you have a space 8 dimension bigger than the image space. You send this space crashed into a smaller space. By doing that, we ensure there's a very, very high probability it has a solution. The 8 comes from there.
I see, okay.
Yeah.
Okay. Okay, and not technical question.
Yes.
So you have a team of independent developers.
Yes.
Been managing a couple of teams. You have to keep the leashes tight.
No, we don't. No.
How do you ensure the quality, delivered by them?
So and this is a very good question. No, we have a trust in those people. I think those are believers. We don't have. I don't check. Okay, very good question. First, I do not write a single line as software the codes. I do not write one, and I could write before, but once I started to do research in cryptography, I decided I will never write a single line of code. Does anyone know why? Because I live in the U.S. and U.S. has something called export control. You all know, right? So in the U.S., cryptography is classified as weapon. Okay, but be very careful. Okay, and the U.S. also has very good law, which is freedom of speech. So that's why I could come here to talk. But I cannot write a product. If I write a single line of code, if I send it by email to somebody run it, I will go to jail.
So exactly 1 year, I want to interrupt right here. Exactly 1 year ago on this stage,
Yeah.
a different stage, but
Yeah.
for Bitcoin Wednesday,
Yes.
our 5-year anniversary,
Yes.
we had Phil Zimmerman
Oh, yes.
and giving a talk.
Yes.
So he was, for those that don't know, he was the person that
PGP.
that discovered PGP and popularized the public key
Yes.
cryptography. And he almost went to jail.
More or
for
less.
the export, right?
Yes.
But,
Yes.
But he took the code and put it into a book. So you can actually write the code
Thank you.
and put it into a book.
Thank you. That's what I'm doing now. So when I started to do research in cryptography, I decided I will never write a single code. I will never touch a single code. My students should do that. So they go to jail, not me. No, I'm serious. So what Richard said is absolutely.
But you can write the code, you just have to put it into the book.
No, that is true. That is true. But you have to be very careful because sometimes you have email, people ask you for this, you just send it out to people, then you're dead. Okay, but one story I heard is some U.S. company, they have encryption software, they want to bring it to Europe, they do exactly what you did, I suggested. They print on paper and then send to Europe and then retype it. Actually, they rescan it and that's done. So that's very interesting. Yeah, so I do not write a single line code. So of course, my partner Andy, so I do not bother to read code. So therefore, we do not, as you said, we are looking for people who believe this, and that's it. They should be self-managed. We do not manage them at all.
Again, I need to say something. Since we had Phil Zimmerman talking for a long time on this, so since that case, code is freedom of speech.
In the paper form, not in the runnable form, not in the .exe file. No.
Go ahead, please.
Yes.
Do you know about literate programming? Do you know this form by Donald Knapp?
I heard a little bit, but yes.
It's a mixture of LaTeX and then inline code.
Yes.
So we also work on a very mathematical project, and we work with something like 10 researchers.
Yes.
But we actually try to implement literally the paper. So we write the paper, which is human readable, but inside bits of it are code. So you can actually take the paper, compile it to a book, or compile it to a runnable daemon. It's the same thing, and this is very nice. For
Yes.
So I just thought it was interesting to mention, especially because of the
Yes. No.
in the book.
I agree. I mean, I agree with you. The U.S. law is really absurd in the sense, By these days, with AI, with whatever, you can read the codes and you can easily read the codes into machine very easily, right? But the law is there. So you have to be extremely, extremely careful.
Thank you. I have a question myself.
Yes.
Then the last question will be.
Yeah.
Ever since your colleague was on stage here
Yeah.
2 months ago, I was
Yes.
interested in ABC Mint.
Yes.
And in your talk, you said something about being ASIC resistant.
Yes.
Do you know that at the moment there are GPU mining rigs being built for ABC Mint, and therefore it's not very decentralized anymore?
But GPU is not hardware. No, be careful. GPU is not hardware. GPU is you write software on. GPU is not. It's not a special purpose GPU for ABC. No. It's not true. They are just building rigs, from what I heard.
There will be mining farms being built.
Oh yeah, mining farm. Yes, mining farm is okay. They just use GPU and put the software on it, but not to build an ASIC machine. Only. No, let me say it very carefully. So the mining farm they're building, you can do it too, as long as you have money, because software we already put on the web page. So you can do it too. It's not, but ASIC machine is different, right? I'm an ASIC machine maker. I spend so much money building it, only I will make it and sell it. But over there's no monopoly on anyone. If you want to spend the money, yes, go ahead. There's nothing we can do on that, about that. But there's no hardware design such that you cannot use it. The other party cannot use it. It doesn't happen yet. Of course, you were right in the sense that there's always a possibility to do hardware implementations. They will be better. But the point is that if you improve only 5 times or 10 times in terms of initial cost of building an ASIC, they might not want to do that. Yes.
Why might we need quantum proof algorithms for anonymity in cryptocurrency?
Anonymity, yes. I mean, so this is a very good question. There are quantum proof anonymity algorithms that exist based on lattices. You can do something like that. There are. Just efficiency may be lower. Yeah, there are zero knowledge protocols and so on based on lattice crypto. Yeah, there are. We can do that, but efficiency is a problem, is concern. But for lattice-based crypto, I'm a little bit concerned in the sense that there's one mathematical problem related to lattice-based crypto. So lattice-based crypto is when we choose the parameters, we have a very, I would prefer to say that we are not so sure, we don't have a very high confidence in the selection of the parameters because there are at least one particular fundamental mathematical problem we couldn't resolve, called the root Hermite factor. I don't want to talk about what it is, but just remember the name, root Hermite factor. And there's something there, it really bothers us. And we have no answer for it. So therefore, I'm very worried about lattice-based crypto, their parameters. That's the only thing I want to say, yeah. Yeah, sure, please.
We also heard about BLS signatures earlier today, and there are lots of other
Which signature?
BLS signatures.
Bliss. You talk about Bliss.
Yeah.
Yes,
Yeah.
that's a lattice-based signature, yes.
Right. And the other, there are like things like, I don't know, cyclic snark constructions and stuff like this. Like,
They are similar, they are not exactly, yeah, there are,
do you have this kind of stuff in lattice-based?
at least for yes, at least the ring signatures, no problem. There's a paper, if you want, I can tell you where it is. There are ring signature based on lattice, done pretty efficient.
Okay, so it's like a lot of, because I always understood that a bunch of the problems with lattice cryptos, that it can do signatures and so on, but like more stranger, newer constructions are not so well.
No, I think lattice the very good thing about lattice is it's very flexible. It can do almost anything as far as I know. Yeah, just we haven't spent enough time on it, I think.
No, of course,
Yeah, but there are at least, so if you're interested.
That was basically, that was the question.
Yeah, yes. If you're interested in doing something like Monero, I know for sure we have some proposals already. Not me. I mean, somebody did some work on already.
Yeah, okay.
Build the ring signatures. Yeah, so that's the basic design principle of Monero, right? The ring signatures. And they have something like that already. But efficiency, of course, the key size. The problem is the key size, which means your transaction size will be very much enlarged. So if you don't care about that, I should be okay, I think. Yeah. Mm-hmm.
One more?
Yeah.
How long do you think it takes before this problem is solved? That we can handle the
You mean for lattice or for?
no, for the quantum computer is not anymore a danger to Bitcoin and so on. How long do you think it will take?
You mean for us? I mean, no, I don't understand your question, sorry. You mean for Bitcoin itself to do it?
Well, at the moment, Bitcoin is vulnerable to a
When a computer attack.
attack.
Yes.
Yeah.
Uh-huh.
And you are trying to find a solution.
Well, we found a solution. I mean, we proposed of a new design already. It's running already. So this is our solution. It's a new blockchain. It's a new Bitcoin. It's a new quantum-proof Bitcoin. This is our proposal.
So when will that be implemented? What do you
It's implemented already. It's running now.
So why don't we have that already?
It's run. If you want to do it, you can go ahead and running it already. It's there already. It's called ABC Mint. If you go to abcmint.org, you can download software. You can run yourself. You can do mining. You can do everything.
Yeah, but that's a totally different coin.
It's a different coin. Yes.
We can make a Bitcoin improvements proposal.
Yeah.
Yeah.
that's
So
what I mean.
yes. No. You can do it yourself already. You can do it. You can do it. You can copy mine the algorithm, try to insert there, try to convince people to use it. You can do it. But the problem is whether people follow you or not. I don't know.
Yeah,
That's a fork. Yeah, you can do it already.
So what do you think will happen?
I think nobody will follow you. This is my opinion. Yeah, because I mean, this number one, they will ask, there are 9 algorithms. Why do you choose this one? There will be a big fight over which one should be the best. Number one, okay? And then normally there are people believe this one better, believe this one, then they do their own thing. So there will be fork. I think that's what might happen.
But something has to be done.
Maybe not.
It cannot last as it is.
I don't know. Yeah, so I just let them decide. I think, you know the recent story, right? Between Bitcoin Cash, right? Bitcoin Cash, and you know all the stories, right? So that's a very minor thing, right? The fight is pretty furious, right? And it become very personal as well. So I don't know. Because the problem with quantum threat is I expect coming very quickly. And if you don't do anything, if you cannot do anything, then you're done.
Yeah, I think so.
Yes, so this is one of my guesses. I believe the quantum computer will be secret, and then what? Boom.
Yeah. Then we are too late.
Then you're too late. This is what I believe. Okay? Nobody will tell you, oh, I'm very close. No.
Well, I'm not so good.
Let's give a round of applause and thank you.
Okay, thank you very much. Okay, thank you.